All right, so this topic, algorithm analysis, we're changing pace a little bit, only briefly. We're going to take a moment to actually talk about what it means for an algorithm to be good. We've done this a little bit in 161, and up until this point, we talk a little bit about things like, oh, if I'm doing a linear search with n things, how many things do I have to look at? All of them, right? All n, right? That's what we're going to get into now, but we're going to get into it a little bit more formally, with a little bit more rigor. That said, it's still going to be kept very high level, so it shouldn't be too crazy for you. We could go into a lot more detail, a lot more formalness. We could get a lot more mathematical with this. We could, but that's going to be like what you hit next year. Right now, I'm just giving you more to take a step in just having a better understanding of like goodness when it comes to an algorithm. So everything up until now was like, okay, we're coding and whatnot, but now let's actually take a moment and like look at our code. Or really look at our algorithms, because this is independent from the code, it's the algorithms. So, you know, we have spent time talking about what does it mean for an algorithm to be good. And when you first start programming, you might think like, oh, less lines of code, but that often isn't a good indicator. Things to me that makes code good is correctness. Obviously, you want your code to be correct. I want it to be understandable. I want it to be readable. But what we really care about is, like, in addition to being correct, but what we really care about when it comes to algorithms in terms of like what makes one better than the other is how much resources, like how many resources that algorithm needs. Or more specifically, how much resources does the algorithm need, and how does the amount of resources needed change relative to the input size? Which might sound like a lot of words, but that's like what I meant, like if I have a list of size 10 and you want to do a linear search, how many things do you have to look at? 10. If I double it, 20. If you multiply it by 10, 100. That's what I mean. The input size is like, well, how big was that list? And how much does the work change as the amount of, like, as the input size grows? Well, the amount that it changed grew linearly. You doubled the input size, it took twice as much work. That's really what we're getting at here. Often when we start talking about these ideas, new programmers, new computer scientists kind of miss the point that we're talking about how much work is required as the input size changes. And they just think like, okay, the input size, it's a linear, there's n things. But it's about how much work is required and how much it changes relative to the input size and how the input size changes. That's kind of what we're getting at here. The nuance difference isn't going to matter too much in this semester, but going forward it'll be really important, like in 255, etc. And so I just said the amount of resources your code takes is what's important. And there's a couple of things we could talk about in terms of resources. We could talk about, well, like how much like compute time is there? And I don't mean like you're running a stopwatch. I don't mean like you're literally timing your processor. It's more about like how many steps are required. Because I could have a fast processor and a slow processor, but the number of like computational steps is what is kind of like consistent between the two, whether or not one has a faster clock speed than the other. Clock speed being like how fast it can do its steps. But we could also talk about how much space your algorithm requires. We could also talk about the number of processors your algorithms require. You might have an algorithm that can run really fast, but it requires like 10 million processors. Well, and you'll notice that as we go through this, all of these things, these resources, tend to be like at odds with one another. It can, not always, but it's common for, like, you know, that no free lunch thing. You win some, you lose some. It requires less computing resources, but it requires more space resources. Requires less computing resources, but requires more processors. Now, for our purposes at this stage, we often like to focus the discussion around like space and time complexity. That's like the time is like the processing time. And space is like how much RAM, like how much space that algorithm needs. We tend to focus on those. And really at this stage, we're going to put the primary focus on time complexity. All right? So when it comes to two algorithms, one algorithm is better than the other if it can do the exact same thing correctly, but has a different time complexity. If one has a better time complexity than the other. When we're talking about time complexity, again, I don't mean that yours ran in 2 seconds and theirs ran in 1 second. Okay, good. But was your algorithm like actually really that different, or were they basically the same and it just took a little longer, whatever? We're talking about like big picture things. Like remember when we were doing the searching algorithms last semester? There was a linear time search. If you have an algorithm that's linear time, that's great, we like that. But remember binary search. Who here remembers how much work the computer had to do relative to the input size on binary search? Log n. With a linear search, if you doubled the input size, you doubled the amount of work. When you have a logarithmic time algorithm, if you doubled the input size, you only had to do 1 more unit of work. That's way better. That's way better. And that's what we mean when one algorithm is better than the other. Now, going back to the linear search, binary search example, there was a catch with binary search. You couldn't always do binary search. What had to be the case for binary search to work? Your data had to be sorted. Otherwise, you're out of luck. You're stuck with a linear search. And that's not bad. A linear search, linear time algorithm, great. But if you can do binary search, do binary search. All right, so the above considerations are all important, but here we're going to focus on what we call time complexity. So the amount of time an algorithm needs relative to the input size. And really, it's actually relative to the input size as it changes, but like how long does it take to sort 10 items versus 10,000 items? Okay? Now, you can't answer this question without knowing the sorting algorithm, but that's what I'm talking about here. And so consider the number of operations needed for the algorithm and the time complexity of those operations, like an addition or a comparison, okay? We're not going to focus on, we could have this discussion of like time complexity at varying levels of abstraction, and we can go down and actually count the number of like CPU cycles, how many floating point operations your CPU is doing for an addition or a comparison. But we don't care about that really. We care about the fact that if I have two numbers and I want to add them together, it's constant time. It's going to take the same amount of time like no matter what, okay? It's not going to change. There's nothing really to scale there. Like, well, what if the input size is bigger? It's addition. It's two numbers. You're adding two numbers. It's constant time. The amount of work, I'll call it even. Even if addition might be a little slower than a comparison, for example, I don't really care. They're both constant time. The amount of time an addition takes and the amount of time a comparison takes doesn't really matter. Like, think of a linear search. How much work does a linear search need if there's 10 things versus a million things? Addition. How much time does addition take if you have two things? 3 things? Well, okay, you're adding 2 things twice. It's you know. So it's constant time. The actual time difference between the two I don't care about. My point is, it's like a fixed amount of time. You know, someone in the room could be like, well, technically if the numbers are too big and you have like a really big number, it could actually take long. Fine, but we don't worry about that. Besides, that's more of an engineering issue, not like a mathematical issue. About like, in theory, what are we talking about here in terms of like, in theory, addition should be constant time, comparison should be constant time. That's what I'm talking about here. Is this clear so far? Or am I going over too fast or way too slow? Do you get the point? All right, I'm going too slow then. All right. With an understanding of an algorithm's time complexity, one can start to make informed decisions about the algorithms they're using and the choice of algorithms and what to use. So, for example, the size of input could be the length of a list to be sorted. How does the time to run the algorithm change as n? Okay, hold on, I skipped it, for example. I went to the wrong example. So with an understanding of algorithms, time, and complexity, you can make informed decisions. First of all, if you have two algorithms and one's just faster than the other, pick it, right? But you'll notice as we go, there's always a bit of a, well, in certain situations, this algorithm's faster, and in other situations, this algorithm's faster, right? So there's always like a no free lunch. There's always like, sometimes there is a silver bullet, there's just a faster algorithm, fine. But often, once you start to get to like the best algorithms for certain situations, it really depends on the situation. So for example, if I know, like with a list, let's think back to a Python list. And I'm just giving you a hypothetical example. A Python list. If I know that the list implementation, I have two options to have a list. Maybe I have an array list and maybe I have a linked list, right? Think of the stack. And I know that, well, you know, with the array list, it's really fast to add things to the end. But with the linked list, it's slow to add things to the end. But you know, I really don't care because the way I'm using the list, I'm always going to be adding to the front more. So maybe I should use the linked implementation because I know the linked implementation is better in certain situations than the array one. If I was adding up to the end a bunch, I should probably use the array one instead. We'll come up with better concrete examples as we go. That may have been a little too abstract at this point. So we start with what we call a growth function. And the only reason, now listen up, the only reason I'm explaining this is so in like 2 minutes I can say you can ignore it, but don't ignore it yet. Everything that we're working towards is based on something called a growth function. It's important to understand the relationship between the input size and the amount of work required. So we have this thing called a growth function. And it tells us about like the time it takes for the algorithm to run. T of n. So T of n is the size of the input, and T of n should be a function that tells me how much work is required for this particular function. So the size of input could be the length of the list to be sorted. How does the time to run the algorithm T of n change as n changes, right? So we need an expression to describe this. If we're thinking back to a linear search, T of n is going to be kind of like T of n equals n. It's just linear. If we have a binary search, it might be T of n equals log base 2 of n, right? So T of n is called the growth function. And notice how T of n is a function of n. The result of T of n, which, by the way, we don't know what the right-hand side of this equation is, but any given algorithm will have a T of n. We can figure out what it is. We'd have to calculate what T of n is for a given algorithm to say T of n equals yada, yada, yada. But all algorithms can have a T of n calculated for it. So this means that the amount of time that an algorithm takes depends on the size of the input. So consider this particular growth function. It's entirely arbitrary. It has no real meaning. It's just some growth function for some arbitrary algorithm. T of n equals 15n squared plus 45n. Okay, that is our growth function. If at any point right now you're thinking like, well, where did that actual 15n squared plus 45n come from? Don't worry about that right now. We're going to talk about that a little later. This is just a growth function for some algorithm. Okay, I've already calculated it for you. So T of n equals 15n squared plus 45n. Let's take a moment, you know, like, let's say n was 1. If I plugged in 1 to that whole expression, I get the result in this column here, like it's 60, right? Why? Because 15 times 1 squared is 15, plus 45 times 1, well, that's 45 plus 15, that's 60, okay? But now we're going to play the blame game. Which chunk of this growth function is responsible for the most amount of work? The growth function, the total, is just the total amount of work, but it's like a sum of parts, right? So which part is to blame for the biggest chunk of the total growth function? So when we look at when n is 1, well, 15 units of work came from the 15n squared part, and 45 came from the 45n part. So clearly, which part was worse when n was 1? Well, the 45. Why? Because 45 is bigger than 15, right? What about when n is 2? Well, the 15n squared is now 60 and 90. Again, the 45n is worse. How about 5? Well, now it's a little different. Now the 15n squared is bigger than 45n. It's still not small, but you know, they're comparable, but we could see that the 15n squared kind of took over. When it's 10, now the 15n squared is starting to really outpace the 45n. And if you know anything about basic mathematics, I don't know, when do you learn about like n squared? Grade 9, if not before that? If you know anything about n squared versus n, if I were to plot these lines on a graph, which one grows faster? The squared. If you take a number and multiply it with itself, it's going to be bigger than just the number. And if we keep going, and by the way, when we're talking about like these growth functions and time complexity, we usually care about when n is a big-ass number, all right, when it's a big number. So I started with 1. No one gives a shit about what it's like when it's 1. People care when it's like 15 trillion. Is that even true? Yeah, billion trillion. So when the input size is 1,000,000, the 15n squared part is 15 trillion units of work, and the 45n is 45 million units of work. In fact, if we were to take what proportion of the total work we could put the blame on the n squared part, that's what that last column is. And in fact, as n gets bigger and bigger and bigger, the n squared part takes up more and more and more and more and more and more of the total work. In fact, look, when n is 1,000,000, the 15n squared accounts for 99.9997% of the total work. The 45n part accounts for 0.0003% of the work. It's nothing. And if I made it 10 million, if I made an input 10 million, it would get even, like the 45n's part of the blame gets smaller and smaller and smaller because the n squared grows so much more rapidly. In fact, I would look at this and say, most people would say, the 45n part compared to the n squared, the linear part versus the quadratic part, quadratic, you know, the n squared. For those of you, by the way, this is a pause. For those of you who's always been like, why do they call the squaring quadratic? Quad means 4. You're right, but think of a square, right? How many sides does a square have? 4. So that's why it's called quadratic, FYI. If you've ever been wondering why the hell, that's why. So the quadratic part is so much bigger than the linear part. The linear part, as n keeps getting bigger and bigger and bigger and bigger, it becomes more and more and more and more and more and more useless, the linear part. In fact, so much so that most programmers would be like, pretend the linear part doesn't matter at all, just forget it. We can ignore that. Like, look, I'm not saying it doesn't exist, I'm just saying, like, it's itty bitty. It looks like you have a question or something? No? All right, cool. In fact, if we show this plotted, I am plotting 15n squared, 45n, and 15n squared plus 45n. Now, it's hard to really tell here, but the green and blue lines, because of the scale, like look at the scale, times 10 to the 13, right? The green and blue lines are basically on top of each other. And the yellow line, which if you're used to any linear plot, a linear line is just like a straight line that kind of like goes diagonal, right? Well, the scale is so crazy big that it looks literally flat, as if it's not growing at all. Okay? The point I'm making here is when we start looking at these growth functions, there's always going to be a part that dominates so much that that's all we care about. 15n squared versus 15n squared plus 45n. The 45n part is so useless that at this scale, the lines look like they're indistinguishable from one another. Meaning that 15n squared plus 45n, I only care about the 15n squared. In fact, I don't even care about the 15. The 15 is just a scalar. I really don't care. That's some like constant amount of work that's associated with each unit of n. I don't care about that. Maybe this plot should also include one where there's no 15 in front. So, Okay. This warning, whenever there's a warning, usually it's good to hit. I'll just read it. One thing students tend to miss when first learning about computational complexity is that the function describes how things change relative to n. Okay, I've been ranting about this for a while. At this stage, the discussion is not about any absolute runtime value. For example, given the growth function n squared plus 999n, one may say that the 999n part of the function is going to dominate all values, but no one cares about that because it's all about as n grows. What's going to dominate? The n squared part will dominate, will always eventually dominate. Someone can say, well, look, in my particular example, I know the input size, in this particular scenario, I know the input size would never be more than like 700. So the 999n part isn't really going to matter. And those particular situations, this is not a conversation worth having, right? You have effectively a constant time amount of work because it's fixed, right? It's never going to grow indefinitely. When we have these conversations, we're talking about algorithms where the input size can grow arbitrarily large. Sort this list. How big is the list? That's an important question. Okay. So now, after talking about the growth function, really what the computer scientists care about is what we call like our big O notation, and we pick what we call asymptotic growth functions. Basically, computer scientists are really lazy. I don't know if you haven't realized this yet, but we are. Hell, we make computers do all our work for us, right? What's that joke? You'll spend 3 days automating a task that you could have just done in 30 seconds, but you've automated it, right? That's how lazy you are. Anyways, we are lazy, and talking about any specific growth function, like 15n squared plus 45n, that's too complicated for us. What we want to do is take our growth function and then say, okay, which of our suite of popular growth functions does this look the most like? We never want to talk about, oh, it's 15n squared plus 45n. No. What I would say is 15n squared plus 45n grows like the function n squared. Computer scientists use a specific set of functions to describe all of our stuff. There are the specific set is it's not tiny, but of that specific set, at this stage, there's really only a small number we're ever going to really look at. Constant time. All that means is the amount of work your algorithm needs to do does not depend on the input size at all. Logarithmic, like log n. Linear. Then we have n log n, so like n times log n. And then we'll have like n squared, n cubed, I guess. But there's really few that we discuss. There are more, but for the most part, we pick from a set of very specific growth functions and we say like, okay, this growth function looks like this one. So yeah, blah, 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 okay, so constants and coefficients and things that are dominated, we don't care about. The actual growth function is not important. We care about the asymptotic growth function. What does our growth function grow like? So yeah, the time the algorithm takes as a function of n will grow like, and in our particular example, n squared. So we would say our growth function t of n equals 15n squared plus 45n, has a big O of n squared. Big O meaning like the time, the order of, like the time complexity is on the order of n squared. And we would write it like this. I'm trying to highlight it, but it's not working. It's probably embedded as an image or something. And the reason it's that is because, my goodness, it grows like, did I just right click on that? Show math as, ooh. Fascinating. I never knew you could do that. Huh. Anyways, now that I got distracted. So example growth functions. If t of n was 17, if you have a function that always takes 17 units of work, I would say that has a big O of 1. Even though you're like, well, no, it's 17 units of work. Well, no, 1 doesn't mean I'm saying it's 1 unit of work. 1 means it's constant. 1 means, so if I have t of n equals 17, and I say calculate t of 1,000,000, it's still 17. Calculate t of 10 bajillion, it's still 17. It doesn't change. Nothing on the right-hand side of that top equation there depends on n. So it's constant time. If I have something like 20n minus 4, I would say, well, that's linear. If I had something that was like 12n log base 2 of n plus 100n, well, that's n log n. By the way, most of the time in computer science, we don't even specify base 2. It's like implied. It's always base 2. Usually you assume base 2 until specified otherwise, which is different than like regular mathematics. In regular mathematics, what do you assume the base always is? Exactly. Very good. Well, they're wrong. We're right. Because everybody likes multiples of 2. 3n squared plus 5n minus 2, big order, big O of n2, n squared. 2 to the n plus 3n, well, that's 2 to the n. Now I'm going to warn you, if you have something that's, if you have an algorithm that takes 2 to the n amount of work, you're screwed. It's okay. That said, I'm going to hit a pause. That said, often, if you have a problem that's so complex that the only algorithm you can come up with to solve that problem looks like that, right? Did I ever explain to this class the traveling salesman problem? Maybe. Does anyone in here have a whiteboard marker or not? All right, fine. We're going off topic, but this is good. This is really important. It's not off topic at all, actually. It's just off book. I'm going to lower this so I can use my paint. There is a classic famous problem in programming called the traveling salesman problem. That's what it's like formally called. So here's the problem. Let's say we've got a bunch of cities. The cities are the circles. Their sizes don't matter at all. I can't manage making the same size. Okay? And you are here. Okay? You're a salesperson. And you need to visit all of these cities. You can get from any, assume there's like a decent road network, and you can get from any city to any city. But of course, depending on the geography, it might take longer to get from one city to another, and so on and so on and so on. So here's the problem you have. You need to hit, how many cities do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect, 12. We have 12 cities. All right? Your job is, you are starting here, you live here. This is where your house is. There. You live there. You need to visit every one of these cities today. You start where your house is. You visit all those cities, and you need to end where you start. All right? Visit each city once and only once. Okay? That's the problem. This particular thing is called like a Hamiltonian cycle, which has a, that's what it's called. It's a fancy name. But do you ever play those games as like a kid, like, oh, draw this picture without lifting your pencil? It's like that, okay? So if I say do that, you're probably going to come up with something like this, right? Go here to here to here, 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 here. Oh, wait, we already went there. Oh, shoot. All right, let's try that again. Here, 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 here. It's probably pretty good, right? But the question is, well, what's the best path, right? This is an example of 12 cities, and humans are usually pretty good at looking at like the spatial stuff and being like, that's pretty good. But maybe this is the best path, right? I don't know. Maybe it should go like this. No, that can't be it. Maybe like this. Maybe that's a better path. It's different, but maybe that's better, right? But you know what? This is all kind of silly because at the end of the day, there's a stupidly simple algorithm to find the best path. Here's the algorithm. Try every possible path, pick the best one, right? Best one being the one that minimizes the total distance. Would you agree that that's probably a pretty damn good strategy, right? That's not a trick question. Try every possible combination, record how long each path was, and then just take the best one. Easy, right? Very easy algorithm. That algorithm is guaranteed to work. It will work. The problem is, how many paths are there? Well, let's talk about this for a moment. Let's try to calculate how many possible paths there are. I have 12 cities, but I'm starting in one, right? I start in one of the cities. I have a decision to make. And for those of you that's getting weirded out by this, you got to go back to like grade 6 when you learned that this is how it works. And if you don't remember that you did learn this in grade 6, I vividly remember learning it in grade 6. Did you ever play those games where you're like, I have 3 shirts and 2 pairs of pants. How many possible combinations are there? Well, you just multiply it out, right? For each shirt, I have 2 pants. Another shirt, 2 pants. Another shirt, 2. So it's 3 times. Anyways. How many? I am on one of the 12 cities. I have a decision to make. Which city do I go to first? How many choices do I have? 11. Great. So let's say, hypothetically, we go here. Now how many choices do I have? Then how many would I have? 8, 7, 6, 5, 4, 3, 2, 1. So the number of possible paths I have is, if I can find my cursor, 11 times 10 times 9 times 8 times 7 times 6, and so on and so on and so on, which is, of course, what you said. What is 10 times 9 times 8 times 7 times 6 times 4. Not what the answer is. What do we call that thing? Factorial. When you multiply every number by its predecessor. So this is a factorial situation. Now, you have to remember, we could get more precise and we could be like, well, okay, so if really it's not n factorial, really it's like, first of all, there's 12 cities, so it's n minus 1 factorial. So we're a little better there. And of course, for every pathway, there's a forward and backwards direction, right? So like with this path, did I go, I can't see my cursor. Did I go here first or did I go here first, right? So for every one, there's 2, so like really there's half that many. But that's the growth function here. We're talking more about like asymptotic complexity. The number of possible paths there are is n factorial. It grows like n factorial, okay? Okay, so how bad is that? Well, with 12 cities, what is 12 factorial? Oof. That's a big number. 497,001,600. Okay, you know, it's a lot. So the algorithm will work. All it has to do is try every one of those 500 million paths and pick the best one. But that's with only 12 cities. That's not a lot of cities. What were you going to say?
It's kind of so bad that I've like, when you try to write a factorial function, it kind of stops working after you get to like 13 or 14.
A lot of, yes. So that's 12 factorial. What's 20 factorial? Okay, what about like, what if we have 100 cities? 100 cities isn't even big. Times 10 to the 157. How many are there in the universe? The universe is a vast range to consider, well, knowing that all matter is composed of extremely small particles called atoms. It is estimated that we are between times 10 to the 78 times 10 to the 82 atoms in the known universe. You could think about this for a second. Humans are really bad with big numbers. So take a moment and think about what this means. You could take every single path possible, every single Hamiltonian path possible for 100 cities, and assign each path to a particle in the universe. And you will run out of the particles really goddamn fast. We have orders of magnitude, so many orders of magnitude more. We would run out of particles hilariously quickly. Combinatorics, man. It's wild. It's crazy shit. So, the algorithm is simple, but its runtime is screwed by the fact of like, well, how many possible cities are there? So this traveling salesperson problem puts us in a bit of a pickle. Because if I told you, go write that algorithm to go and solve the fastest, like the shortest path for 100 cities, it would take longer than the universe has existed to make a dent in evaluating it. Think about that. It would take longer than the universe has existed. I'm not being silly. This is simple to calculate how screwed we are in these situations. This is where AI often comes in, right? I know when we talk about AI today, we're talking like, oh, ChatGPT and shit, right? Well, yeah, that's part of it. But a lot of AI is dealing with problems like this, where it's like, we need a way to solve this problem. And we go like, shit, let's try this. A lot of AI comes down to going, look, we know we aren't going to find the best solution, so don't even try. Just come up with a good enough solution, right? That's a lot of what AI is. And you know, you really shouldn't think, if that makes you think like, man, we're shitty, like we're really like kind of putting our eggs in that basket, from like the starting position of like, look, We know we aren't going to get a great answer. We're just hoping to get a good answer, right? We're starting from that position. But take a moment, and I want to be very clear. With the example I'm about to give you, you might feel the need to be like, oh, that's kind of like a silly contrived example. It's not. It's literally the same shit. Every single one of you in here walked at some point today, right? You walked. I'm walking right now. I know how to walk. Some encoding, some mechanism exists in my brain somehow that lets me know how to walk. There is some algorithm in some form that is taking place and being executed in my brain. Pause on that. When I say something like your brain is a computer, I'm not being silly. I am saying by definition, technically it's a computer. It is absolutely a computer. And anyone who argues otherwise, often you get neuroscientists that are like, well, no, it's not. I'm not talking about the box sitting on your desk. It is a computer. There's no ifs, ands, or buts about it. Your brain is. It's got states, it stores information, it can retrieve information, it can process things based on states. It's a computer. It performs algorithms all the time, all day, every day. There's a lot going on. And I know how to walk. I've got some encoding on how to walk. How many of you, raise your hand if you can walk. Okay. Have you ever tripped? Oh, you suck at walking then. We all know how to walk. There may or may not even exist. I wonder, do you think that there is a human on the planet that could be specified as, objectively speaking, the best walker there is? There might be, maybe not. Or maybe that's a stupid question, because maybe there really is no such thing as a best solution to walking. We just need to be able to walk. Your brain never searched for the best walking configuration. You just kind of figured it out, good enough. Now let's learn to run. That's kind of the same idea with AI. Look, good enough, next. Give me the next problem to solve. So we all operate like this, whether you like it or not. Your brains are using these heuristics all the time to just get a working solution done. So that's where AI comes up a lot, where it's like, look, we just need a solution. It needs to be good enough, and then we move on. So what if I trip every once in a while? I stumble, I hit my toe on the steps walking upstairs. Oh, well, whatever. I still walked. Nothing about what I said was like a silly analogy. It's all quite literal, to be clear. You may not have really thought of these things like that before. You may have felt it was too cliche. And don't get me wrong, there are a lot of cliche talks in this space, but we can have serious conversations in this space. Anyways, long story short, there's some problems out there where if your algorithm is 2 to the n, or n factorial, which is really goddamn bad, you might need to start looking elsewhere. All right, where was I? Oops. All right. Okay, some growth functions. Yeah. So here, let's quiz you. Oh yeah, okay, here. Here's a list to the Wikipedia article on big O notation, and in here you'll see the common ones. It's not a long list. Look what's the worst. N factorial. C to the n, that would be 2 to the n, where c is some constant. These are your typical ones. Of these, the ones we really usually care about are constant, logarithmic, linear, I have never heard this phrase before outside of, and I asked so many colleagues, they're like, I've never heard of that before. N log n. And then you got your quadratic, and then you have polynomial where it's n to the power of some c that's bigger than 2. So here's a quiz. 5n squared plus 3n. What would it be big O of? Squared. Why? Because it's bigger. You've caught on. Remember, I told you, the computer scientists are lazy. You shouldn't have to think too hard about any of these ones. N cubed plus log base 2n minus 4. What do we got? N cubed. 10n log n plus 5. N log n. Each term is separated with the pluses. Anything multiplied together is kind of like stuck together. 3n cubed plus 3n squared plus 3. N cubed. Why? Because the cubed is worse than the squared. And then 2 to the n plus 18n to the 10. 2 to the n. It might take a while. N might need to get very big for one of these to dominate, but one of them will start to dominate and will continue to dominate. So with all that said, and I had all this hand wavy of like, oh, here's some arbitrary growth function. Well, how do you actually, like, look, I'm showing you that it's easy to go from a growth function to the big O. But how do I get the growth function to get to the big O? Well, that's where we look at the code. And usually that's the answer in this course. Okay, for simplicity, constant time statements will be said to take 1 unit of work. In reality, it might take more, but it's all going to be constant time, so we're sticking with constants. So if I just had regular old statements, like int x equals 0, y equals 1, z equals x plus y, we will say they're all 1 unit of work. Even though the addition would probably take a little bit more work, it's all constant time. Meaning, what if, so t of n here, I would say t of n equals 3. 1 plus, it's 3. Okay? And if you're ever wondering, but why is it constant? And I'd say, okay, well, tell me what t of 1 is. It's 3. What's t of 10 million? It's still 3 because t of n equals 3. It's always 3. Nothing about this depends on an n. It's 3. It's constant. We're going to stop here because I see people like looking at notes and I'm wondering if they've got a test, and I'll give them time. So we'll wrap up here. We'll have some fun on Friday.